Hi, let's continue the electromagnetic induction part 2. To help students to understand, let's try self-induction experiment. The effect of the self-induction can be demonstrated by the circuit shown in figure. Initially, variable resistor R is suggested so that the two lamps have the same brightness in their respective circuit with steady current flowing. When the switch is closed, the lamp A2 with variable resistor R is seen to become bright almost immediately, but the lamp A1 with iron coil L increase slowly to full brightness. The effect can be shown by the graph of current I against time t through both lamps in figure. The coil L undergoes the self-induction and induced EMF in it. The induced or back EMF opposes the growth of current, so the glow in the lamp A1 will increase slowly. But the resistor R, however, has no back EMF, hence the lamp's A2 glow fully bright as soon as switch S is closed. This is the answer why conventional bulb filaments are built like a solenoid to prevent current from rising in a short period of time and damage the filament. The real function of the inductor device is to store energy in the form of magnetic field. Let's look at the derivative of the energy stored in the inductor through mathematical approach. Let's consider an inductor of inductance L. Suppose that at time t, the current in the inductor is in the process of build up to its steady value at rate di over dt, and the magnitude of back EMF is given by E is equal to L di over dt. And we know the electrical power P in overcoming the back EMF in the circuit is given by P is equal to IE, and let's substitute E by equation L di over dt. Therefore, the product between P dt is equal to Li di, and we know that P dot dt is equal to du. So du is equal to Li di. Therefore, the total energy stored in the inductor U as the current increase from 0 to I can be found by integrating the equation as shown below. At last but not least, energy stored in inductor U goes as a half Li squared. We can make an analogy. The energy stored in capacitor in the form of an electric charge or in terms of potential difference, and the inductor stores the energy in the form of magnetic field whose magnitude depends on the change of current. Now, we have come to the end of the topic. We will discuss the basic concept of mutual inductance. If the current I1 changes with time, the magnetic flux through coil 1 and 2 will change with time simultaneously. Due to the change of magnetic flux through coil 2, an EMF is induced in coil 2. This is accordance to the Faraday's law of induction. In other words, a change of current in one coil leads to the production of an induced EMF in a second coil, which is magnetically linked to the first coil. This process is known as mutual induction. Mutual induction is defined as the process of producing an induced EMF in one coil due to change of current in another coil, and at the same time, the self-induction also occurs in coil 1 since the magnetic flux through it change. To help students to understand, Let we play around and consider two solenoid P and Q arranged coaxially close to each other as shown. At the moment when the switch S is closed, current begins to flow in the solenoid P, producing a magnetic field inside the solenoid P. Suppose that the field points towards the solenoid Q. Based on the right-hand grid rule, we find that the flow of current on the solenoid will generate the northern and southern polarity on the right and left solenoid respectively. Each represents an increase in flux that occurs when the current changes. Since solenoid Q is close to solenoid P, it will also detect an increase in the flux that occurs. The magnetic flux through the solenoid Q also increase with time. According to Faraday's law, an induced current due to induced EMF will exist in solenoid Q. The induced current flow in solenoid Q must produce a magnetic field that opposes the change producing it, which is increasing flux. Hence, based on Lenz's law, the induced current must flow in the direction that will oppose the rise of flux on solenoid P by increasing the north pole on the left side and the south pole on the right side of the solenoid Q. To fulfill the needs, according to the right-hand grid rule, the induction current in solenoid Q should flow in the direction of anticlockwise based on the way solenoid Q is wound, and the galvanometer will show a deflection.